Assalamualaikum and good day everyone. Okay, now we have come to the week 3 of our lecture. Okay, what we have learned so far in the previous lecture. In the week 1, we have studied about preliminary on mathematicals, which is on the vector, orthogonal coordinate system and also vector calculus. And the week 2, we actually learned about electrostatic field. Okay, week 2 is the beginning where we learn about electric field with a static charge. Okay, so what we have learned so far, okay, we have learned that we can have a 3 conditions of charge whether with rho L, line charge density, or with rho S, surface charge density, and the other one is what? Rho V, volume charge density. Why we use this? Because we want to find the electric field intensity. We also know that E can be found from F over Q. This is the charge in which the E field acted upon. Okay, then what we have learned so far, F can also be derived from Q1, Q2 over 4 pi epsilon naught R square, right? And it is vector unit, so you provide a unit vector going to R direction. Okay, taking general representation of rho V. Why we take rho V? Because rho V also contain the line charge and also contain the surface charge in it. Okay, so rho V can use as the general representation. Now this, we go forward to the next lecture, which is the week 3 on flux density and divergence theorem. In week 3, we're supposed to learn the introduction to the electric flux density, application of Gauss law to calculate the electric field intensity for symmetric charge distribution, introduction to divergence concept and the divergence theorem. So this is pretty what we need to cover in week 3. So before we cover all, okay, we learn about this first. Okay, the introduction to electric flux density and the applications of Gauss law to calculate the electric field intensity for symmetric charge distribution. Okay, in Sadiku page 134 section 4.5, okay, you will get to know about D epsilon naught E. E, as you know, is a vector This is a constant, the dielectric constant of free space. So if this is your E vector, and you have this as your vector as well. So what is your D? D is actually electric flux. Density. Now you get to see this way, right? So the symbol of flux is like this. For electric flux, you can put further notation. Okay. Now, what is actually electric flux? In SI unit, one line of electric flux emanates from 1 coulomb and terminates on negative coulomb. Therefore, the electric flux is measured in coulombs. So, what does it mean? For example, let's say you have a charge. You have two charges here. Okay? Let's say you have one charge with 4 coulomb charge, and the other have 7 coulomb charge. So how many is the electric flux? Electric flux is just like electric lines. So you have here, you have 4 correspond to coulomb charge, and here you have 7. So by the graphical representation, you can see which have more electric flux. Is it A or B? Certainly is the point charge B, correct? Electric flux is a scalar quantity. Means it doesn't have direction. Imagine we have a spherical surface. X, Y, and Z. Imagine that you want to take a sample of a surface here. Which we can take as ds. Okay? Now, you want to see how much flux, how much electric flux density. Okay? So let's say you have a point charge here. Okay? Now you want to measure how much is the electric flux at this sample. So this is a surface, and you have your ds here. Then you have your electric flux density. Electric flux in relation with electric flux density, you have D. As what I mentioned earlier, flux is a scalar quantity. So you have here ds is vector and d, what is d? Let's say we didn't know yet. So you see here is scalar, here is ds, vector of ds, the sample of our surface. Because it is scalar, so this one in relation with this one need to produce scalar quantity. So which we will use a dot product or a cross product. So certainly is a dot product and a electric flux density in a vector. Okay, because in dot product it will produce scalar for vector dot vector. Okay, now is it correct here, or are we finished yet? No. Okay, because this is a surface, not a point charge. Not a point, but it's a surface. So we need to use a continuous, which is a continuous condition. So we need to have integration. And this is ds, right? Surface. So it is surface. Surface will involve how many times of integration? Double integration. Okay. We're taking the generalization of using rho v. Okay. As a generation for the point charge and the line charge. Okay, now we go back to this equation. Okay, d unit flux density is equals to epsilon naught vector of electric field intensity. So here, using the volume condition, okay, so you have triple integration rho v dv 4 pi r square and ar unit vector. We should know that this means the direction, means the magnitude, and this one is the vector divided by the magnitude. This one depends on the situation of the questions. Okay, and drop down here you have epsilon naught times with this. So the relationship between d electric flux density and electric flux intensity is related by the constant epsilon naught. Okay, so far so good. Okay, now let we go to the question. We see practice 4.9. A point charge of 30 nanocoulomb is located at the origin while plane Y carries charge 10 nanocoulomb per meter square. Find D at 043. Okay, so put the book away. I have ready the question in the pencil so that we don't have to repeatedly refer to the book. Okay, I hope it's clear. Before we solve the question, it is better always to try to imagine how is the situation. Okay, so we have blue color, pencil, black color, and highlighter. Okay, I hope it will help to distinguish the view. First, we do the axis. Okay, next, it says a point charge of 30 nanocoulomb is located at the origin. So where is your origin? Origin is 0, 0, 0. Correct? So you put a point charge here. We can put as a label Q1. Okay? And so that we don't miss it in the text, we can put here Q1 is 30 nanocoulomb. Okay, finish there. And then we have another one. Second information, while plane Y carries charge 10 nanocoulomb per meter square. Okay, what does it mean by plane Y3? Means in the Y direction, it is always Y equals to 3. And it's a plane, means it is two-dimensional. Okay, so Y equals to 3, so we take Y3, for example here. Okay, so we draw an area that we're passing through Y equals to 3, okay? Forgive me if I don't really have a good drawing skill, okay? Yeah, that's why I'm not an artist, okay? So I hope it's still a good drawing, so that I hope it's still good that you're able to imagine it. Okay, so here plane Y equals to 3 carries the charge. Okay, so you now know that the second information, it is a surface, right? Surface means you will have surface charge of rho s 30 nanocoulomb. Forgive me for this one, sorry, it is rho Q1. Okay, sorry, my mistake. This is your Q1 and this is your Q of the surface. Okay, now the question is asking find D at 043. Okay, first, you know it given the position, the sampling position, which is 043. Where is it? Where is 043? This is your X, so it's 0 here, 4, and it is 3. So for better view, I just it is not to the scale, but for us to easy view, let's imagine this one is y equals to 4. Okay, then let's imagine that here is 3. So where is your area that you want to measure the electric flux density? It's here. So we want to measure the D here. Okay, the question wants us to find the D at 043. In this condition, you see there is two sources of charges. One coming from the point charge, and second coming from the surface charge. Okay, so your answer should be total D electric flux density is a total electric flux density coming from the point charge and also coming from the surface, from the plane. Let us go slowly, okay, systematically. So now we try to solve for dq first, okay. Before that, we say to ourselves that we know that D is actually epsilon naught of E electric field intensity multiplied by your dielectric constant in free space. So we solve from this, then we get the answer of dq by simply multiply it with this. Okay. We know that our D here is 0, 4, 3. Okay. Now, settling for your dq first. Okay. First, for easy view, we can try to draw where is the electric flux intensity that is experienced at this point from the point charge. So it's this one, right? So this is your E due to the point charge. So this is also your direction. Okay, from the EQ, from the equation that you know, is actually Q, in this case, Q1 over the 4 pi epsilon naught of R square in the direction of unit vector R. Then try to solve for unit vector R. Remember, origin is 0, 0, 0. Okay. So you have 0 minus 0, 4 minus 0, and 3 minus 0. This is the movement of vector in x component, y component, and z component. And what is the magnitude? Is simply a square root, right? 0 square plus 4 square plus 3 square. Then you get is actually 0, 4, 3, 5. insert into this equation. You know your Q1. What is your Q1? Is 30 nanocoulomb. Okay, so we can put the nanocoulomb away later on. Okay, we will calculate it later on again, so that it won't disturb us in the calculation process. Now we have 4 pi epsilon naught. Then your R, you know your R, this is your R, right? Is 5. So here is 5 square. Then it is 0.43 of 5. So far so good? Okay, now taking out the epsilon naught here, because we're going to multiply it later on, it will vanish. Okay, so we just put it away. So you left with 30 nano, 4 pi, and 5 to the power of 3. And you have 0, 4, and 3. So what is this? This one we can put it later on also. Okay, remember your answer later on will have a unit of nano and coulomb per meter square. Okay, so remember this, don't forget the nano. So to simplify the calculation, we put the nano away for now. Okay, you can put it here if you want. Okay, 1 nano. Now 30 divided by 4 pi times 5 to the power of 3, right? Then you have 0.020. Okay, I just round it up, and 0.43. Now we put it inside here. We put it, we expand it. Then you have 1 nano epsilon naught, 0.02 direction of x plus 0.08 plus and 0.06. Okay, we know that dq is actually epsilon naught of EQ, right? So we can just cancel out this. Then you will have 0.02 x direction plus 0.08 y direction plus 0.06 z direction nano coulomb per meter square. So this is the unit of the unit of electric flux density. Okay, we only so far we only solve for dq, right? Okay, now we try to solve for the ds. If you notice, for the ds, it doesn't mention the limit. of the plane y. So actually this surface is considered as infinite sheet. Okay, so means it is limitless. Okay, you have limitless, so you can put as the dash line here. Okay, so it is limitless. So when it is an infinite surface charge, infinite sheet, so you can use unique equation. Okay, you can refer to the study book, page 125, equation 4.26. Okay, you will be introduced to the electric field intensity for infinite sheet case. So it is E equal to rho S over 2 epsilon naught A direction of n. Okay. It looks simple, but we must know how to use it. Okay. So here, what does it mean by this? This is actually normal to the surface. Okay. So here, where is the normal to the surface? This is your sample that you want to sample your D. So the normal to it is here. Okay, normal. So this is to be your distance or your magnitude. You can put here the normal directions A. Here is your A, unit direction, unit vector of A normal to the sheet. Okay. Now, this one we have no problem, and this one we have no problem. But how we going to solve for this one? So A unit vector normal to the surface charge is actually okay. What is the point here? It is certainly 0. It is at y3, and it is coincide with z3. So your vector is actually 0 minus 0, 4 minus 3, and 3 minus 3. For the magnitude, simply 0 square plus 1 square plus 0 square. So you actually have this one cancel out is 0. This one is also cancel out 0. So you only have y component with a magnitude of 1. So your E due to the surface, okay, is rho s 2 pi epsilon naught y1. Okay, I put 1 here so that you can see, okay. Then what is rho s? What is our rho s just now? Our rho s is actually 10 nanocoulomb per meter square. Okay, this one you can later on we going to use we consider the units, and 2 epsilon naught y. So 10 is actually 5 nano, then you have this. Okay. So far so good. Now you know that from this equation, ds due to the surface. So a 5 nano unit vector direction. Can you guys help me to calculate what this is? I think there is some mistake in the calculation. Let me try again. Wait for a while, I try to cross check. Yes, there is a bit error there. Okay. So this is actually correct. It is 0.02 is correct, but when I multiply, I multiplied wrong. Okay, sorry for that. So 0.02 times by 4. You have 0.08. This one consider 0, okay? Consider 0 because it is x is 0 here. 0.08. And then now 0.02 times by 3 is 0.06, so it's correct here. Okay. Okay, now we proceed. Now we summarize. Okay, we have D is equals to D electric flux density from due to point charge plus electric flux density due to the surface. Okay, we gather. Now we have your dq here. 0.08 unit direction of y plus 0.06 unit direction of z. Okay, this is coming from the q. The next one, you have your ds. Where is your ds just now? Okay, your ds is here. Sorry. So it is 5 nano coulomb per meter square. Okay. So here you need to addition accordingly to the same direction. So here it's actually 5.08 unit direction of y. Here is z. This is the only component of z. Then don't forget to write the complete symbol with the units. Okay, nano coulomb per meter square. So this is your total D electric flux density at this point. Okay. So let we see the answer. Do we get the answer correctly? This is our answer, 5.08. Here is 5.06, 0.067. Okay, so it is correct. Okay, someone were asking me, okay, that is it okay that my answer have different answer than the schematic answer? For example, is this case, right? Okay, for me, and actually there is nothing wrong. Okay, you can write it this way, 2 decimal places or 3 decimal places, unless if the question specify you, let's say write your answer up to 3 decimal places. If that is the question requested you to do, then this is correct answer and this is wrong. Why is this wrong? Because this is only 2 decimal places, and the question also may ask you like up to 3 significant figures. If there is 3 significant figures, then this one is correct because it's 3 significant figures, and this one is wrong because this is 4 significant figures for this particular y. Okay, this one I don't touch about this one. So unless the question require you to state your answer in decimal places or significant figures, you can actually write your answers in how many decimal places you want. Okay. Thank you. We will continue to the next lecture. See you again. Have a nice day.